Awesome. Welcome, everyone. This is Deep Learning Adventures, a fun and engaging meetup where we tackle deep learning and data science challenges in general each week. For the last couple of weeks, we started a new adventure based on Kaggle courses. If you haven't seen them before, if you're not familiar with them, it's very short, really fun to do learning modules that take you from anything from machine learning to deep learning to data visualization to feature engineering to different aspects of data science in general. So we started that last week with an introduction to Python. And this week, we're going to do an introduction to machine learning. We're going to talk about random forest and decision trees and so forth. There's a little bit of content, so hopefully we'll have time to also answer some questions. And I encourage you to also enroll for the course. It's free. You can take it. It's on Kaggle. And in the end of the day, when you complete all the courses, you can get a certificate from Kaggle as well. Cool. With that said, we don't have a lot of slides put together for this. We want to dedicate as much time as possible to the content itself. So I'm joined today with my great colleagues and co-organizers, David and Robert, and we'll kick it off with the first three modules, then the next three modules, and then I'll come up with the last three modules. So, David, I think you're first for the first three modules, if I remember correctly.
Yep.
Awesome. If you don't mind muting yourself, and if you have questions, we'll stop in the end for questions. You can unmute yourself or type them in the chat box. That'd be awesome. Thank you. The floor is yours, David.
I need to be able to share.
Oh, I just allowed it. There you go.
There it is. Okay. So as George said, we're starting the course Intro to Machine Learning. This is our first chance to actually get away from the Python language syntax and actually start to talk about how we learn and use data. So the first lesson is, I'll dive into here, and I hope everybody can see this. It's big enough. Okay. So the first lesson is just an intro to how models work and the concept of what a model is in terms of this. For some of you, this may be very straightforward, but there's kind of a formula that we're going to go through here where we basically have some data. We choose what we're going to try to do with that data, and we look at the data, and then we format the data for a particular type of machine learning model, which we then train on our training data. And then after it's trained, we're ready to make predictions. So we're going to go through some of that. So the first thing we're going to introduce is what is a model. It's an interesting concept. The example they give in here is basically a one of trying to predict real estate prices, in particular houses. And the first model they talk about or concept is something called a decision tree, which if you're a CS major from years ago, you probably seen these in terms of programming. But the idea is that if we tell it we've got a number of houses and we want to try to predict the price, and those houses have certain characteristics, one of which may be the number of bedrooms in the house. So in the first box here, we're going to look at a decision where we make depending on how many bedrooms are in that house. So a certain characteristic of the data. And so we're going to ask a question about that data in this box, and we're going to get a yes and no answer. And based on that, we're going to make a price prediction. And for the simplistic approach right now, our model says, if it's 2 bedrooms or more, if it's more than 2 bedrooms, we're going to say it's the higher price, 188,000. It's just less, we're going to predict that it's the lower price. And this sort of makes sense. The idea is that we are going to see if this holds true for every house in our data by doing fitting, where we look at our model and train on the training data and see how we do. And then if we don't do so well, maybe we need to reverse this model and say, well, it has more than 2 bedrooms, then the answer should be that it's a lower price, or the price is much different than what we have here. So there's a couple of different things you could adjust, right? The prediction that it makes, and also the kind of the order in terms of which one is higher price and which one's lower. So there's a lot of things that could learn from the simple model. We can improve this if we look at multiple decision trees where, as I was talking about, we've changed the values, and then we run these through our training set and see which decision tree choice here or configuration of our model does the best job. And we would hope it probably is the first one here, where for more bedrooms typically equals a higher price value. And you can imagine then we can bring in other, what we call features of the data, other factors, other information. So again, we're going to look at if it has 2 bedrooms, and we're going to use our model that we already trained in terms of yes and no. But then after we've done that decision tree, we're going to look at lot size. So, you know, is the lot larger than 8,500 square feet? When we've got 2 or less bedrooms, we're going to base a different price there. The price, if it's smaller, it's going to be lower and higher. And the same thing over here, when we have a house that's 2 bedrooms or more, we're going to base different prices on that. So that's another prediction. We're going to adjust this in terms of our model and see how it does on the data. And that idea of going through and adjusting these decision points in terms of like, is 8,500 square feet the right value to use here, or should we use 8,600 square feet? Should we use 3 bedrooms instead of 2 bedrooms here? That's where the model is adjusting the decision points, and typically we would call that in deep learning, the weights and biases are going to be adjusted. But right now we're just talking in terms of decision trees and these values. So that's where we're fitting it to the training data. Any questions on what's going on here in a model like this? Sorry. Okay. So let's talk about what we might do to learn about our data and learn what features we might want to use to make our predictions. Here we use 2 logical ones in a domain that we're all familiar with, which is the price of housing, and you know, a lot of times we're in domains where data sets are brand new to us, and we need to look a little more closely at what we've gotten. So let's go to the next lesson, which is data exploration. A lot of times people refer to this as EDA, which is exploratory data analysis, and it's a big part of doing machine learning. One of the tools that is often used is a nice library, and there's a whole course later that we're going to go through called Pandas. Pandas is a really nice way to bring data from many different file formats into our environment, and then do some really nice analytics around that data. And we can do transformations of the data and things like that very simply with Pandas. But the way you bring Pandas in is import Pandas as PD. And I won't go too much into how Pandas works, but here we're going to read some other housing data for Melbourne, and it's going to be kept in a CSV file, which is a common way for data sets to be brought in. Pandas has a nice little method or function for reading that, read CSV, and you just give it the path to the file you want to read in. And what results is what's known as a Pandas data frame. And again, in the Pandas course, they'll go through this nice object called a data frame and what you can do with it. It's very powerful. You can think of a lot of the Pandas utilities have a lot of functionality similar to what you do in SQL. So if you're familiar with databases in SQL, Pandas can be thought of sort of like a database table that's in your environment. One of the things we can do is call this describe method on the data. When you call describe, it's going to give you what the headers up here are going to be the columns of your data table, of your data frame. So here we've got the number of rooms per house, the price, which is what we're going to try to predict. I don't remember what distance is exactly. Postcode, where it is, bedrooms too, and this, I think these are sizes probably or something. And usually car has to do with like how many cars fit in the garage, things like that. But although there's a huge number here, so I'm not sure what that. Oh, that's the count. That's the number. So we've got, basically this is telling us we've got 580 rows in our data frame. And then for each of these features, here's the mean value, the standard deviation, the minimum, and then the quartiles and the max values. The one thing I will tell you is the scribe will only perform this for features, in other words, columns that are numeric. So if you've got categorical data, Boolean data, you're not going to see it in this output. So just keep that in mind. And then they go through what all those mean. I just kind of went through them with you. And then we look at our first coding exercise. It's pretty much asking you to do what they just went through in that example. And I just want to ask if anybody had any questions about that basic data exploration that you can do and maybe how you input the data.
Yeah, please feel free to unmute yourself if you have any questions.
And if anybody sees anything in the chat, George or Robert, please feel free to go ahead and ask me.
We're taking a look, definitely.
Okay. So here's the exercise that goes along with that learning module. They're going to set up some imports for you, but the first step again is they give you the path of the file, and then they want you to read it in. And we learned before that with pandas we can do a read CSV on that path, and it'll fill in a data frame for us. The next thing to do is to do some exploratory data analysis. As mentioned before, they run the scribe, and I'll actually run all these so you can see. They'll run describe, and it's going to give you those values for every one of the features that is numeric. And there's quite a few in this data set. You'll also, they ask you to pick out some of the values that you get from that. And just, so that's another thing, how to interpret, how to look in there. I got something wrong. Oh, well, have to look back through that. And then they ask you some questions about this data. And the reason they're doing that is they want to make you think about, in the future, we're going to talk about doing more with those features. So you can build, out of features, you can build more complex features that your model might learn more from. It's very important for machine learning to do feature engineering, is what it's called.
If I can guess, the reason you have an incorrect value up there is that you did this assignment too long ago. And
I did, yeah, and I think that's what, I think they've changed. I noticed a few things where they've changed stuff since I last passed the course.
Well, I think the thing is they actually ask you to input a number based on the current year minus the date in which it was built. So if you did it last year and wrote in a 9,
yeah. So I could have actually written the equation out here and it would have worked.
Right.
Instead of doing it in my head. Yeah, you're right. You're exactly right. So now you know when I took the course. All right, so any questions on that? It's basically just showing that you knew what they said in the first one. So that's basic data exploration. And then the next one is machine learning model. And I'm going to go into this a little more detail. So as we mentioned, you will first select data for modeling. Again, they're going to use this Melbourne data set and the similar. And the nice thing about data frames is you can do this columns attribute, and it'll print out all those headers of those columns that you have. And we saw those before, but here they are in an indexed list. Now, one thing about this data set is it's missing some values, but you wouldn't know that unless you scroll through every row in the data set, which would take you a long time. So a quick way to figure out if you're missing any values is to do something called the data and the dot is in a, and do a dot sum, and maybe I can show that on the exercise to see the values. But they know that there's some missing values ahead of time here. They've already told you that, and they're going to show you how to handle those. And what they're going to do is this axis equals 0 stands for row. So they're going to drop every row that has a missing value in it. So.
And that missing value could be anywhere in any of the fields, right, David?
It could be any field, numeric, categorical, anything in any row. So any row that has a column with a missing value, they're going to drop it. Would have been nice if they showed us how many actually were removed, but. And then we're going to set a prediction target, which is the column value, the cell values for each column that we're going to try to predict. In this case, we're trying to predict the sales price, which is price in this data set. And we're going to set a series, actually. This is going to return a series of Y. So this will return a pandas series, which is a similar, you can think of it very similar to like an array, but it's got, it's more like a dictionary in the sense that it's got index and values. So it's a typical series. We also want to choose which features or which columns we're going to actually use to make our predictions with. I think you saw up here, there was a lot of columns. Maybe some of them don't add that much value, or we don't think they're that important, and we can always test that by using them or not using them. Maybe the date of sales, maybe this is the date of the sale of the house that it was on. Maybe you don't think that's important. It might be, I don't know. Let's see, they've chosen to use in theirs the number of rooms, the number of bathrooms, the land size, basically lot size, and then the location. So they're going to use these 5 features to try to predict the price. And here we're just making a list that lists those features, and we're going to select them from the data frame by putting in the brackets here, which is a way of selecting in a pandas. This is a shortcut for just those columns, and it'll return a data frame to us, which we're going to label as X. Since it's a data frame, we can use describe on it. And now we'll see again that these happen to all of the numeric columns, and we can get these values, right? So that's nice there that we can look at what we've got. We can see here that we've got a count of all these, and they're all the same and well-defined. So, and then they run, if you're familiar with Linux, there's a command called head and tail, where you look at the tops and bottoms of files. Well, data frames has that same concept. You can run the head method, and by default, it'll give you the top 5. But if you run, you can put a number in here and get any number of rows that you want to see at the beginning, at the start of the data frame. And if you use tail, it's the same concept. Sorry. So here you can see these are houses that maybe, I don't know if they're close or not, but it's, there's no specific order here in the head. It's just going to be whatever you read in. So I talked about this formula early on for how we would do machine learning. First, we define the kind of model that we want to use, what's appropriate for doing our prediction. The type of prediction we're doing here is called regression, where we're predicting a single number, the price of the house. So that's called a regression. And there's certain models that are good for that. We're going to then, after we define our model, we're going to fit our training data so that we're trying to have the model adjust its parameters to be able to make the best predictions it can. And hopefully it captures some patterns in the data that help it with that. And then we're going to do prediction to see how our model, what it puts out. And then the last thing is to evaluate how good your predictions are. And we won't go through the evaluation methods that much here. We're going to go through the basics of defining, fitting, and predicting. Evaluation, I think, is covered in the next course 4, I think. And there'll be more different kinds of models that we'll be able to choose from in the future as we go through them. I'll tell you the first one we're going to do here is called a decision tree regressor. and it performs kind of the decision tree that I showed at the very beginning about how models work. And it's a regressor, meaning that it's predicting that it's a regression. It's suited for a regression problem where you've got one output, which is the numerical value that you're trying to predict. So the first thing we do is import it. It's from sklearn, which is a really wonderful library for doing machine learning and many other things for handling, transforming data and working with data. It also has a great set of metrics for evaluating different models. So even if you're not doing, if you're doing deep learning, it still has very useful metrics and very useful utilities for working with data, particularly pandas and NumPy arrays. So we're going to initialize that decision tree regressor. They're given it a random state, which is like a seed for the random number generator that helps it work. This is so you would get, if you ran this recurse a bunch of times, you get the same results, and they're going to, later on be checking your results in the exercise. So we want to have that be consistent. For almost any type of model, when you do your training, you use what's called a fit routine. And the first two arguments are almost always your samples and your labels. And typically those are the X values that we set earlier to all those features, and the Y, which is the sales price on each row. So that's what's being put into our fit. It's going to run and adjust all the values it can adjust to make the best fit to this training data to get the closest it can to those results. So that runs, and the next thing we're going to do is try to make some predictions. So we're going to look at, we're again just going to see how it does on the data that it is trained on. So this is not typically how you would evaluate your model, but just for this initial run through and learning, we're just going to look at how did we do on our training data. Typically you don't get exact answers, but you get pretty close if you trained well. Here they're just printing out, remember what we had in our first 5 values and what those predictions are going to be for those first 5. So we're feeding in 5 rows, 5 houses, and here are the results. This first house looks like it's not that big. Probably one of the smallest, maybe the next one. Yeah, given the lot size, it's probably the smallest house on the smallest lot. So you would logically think it would have the smallest price, and it does. Maybe number 4 or 3, let's see. Maybe number 6 would be the highest price based on the lot size and the fact it's a pretty good size house. And that seems to be the case. We don't know we don't know a lot of other information, maybe one's a rundown shack and one's not, but they didn't do that to us here. So it seems to be following these were good choice for features, right? So that's kind of, any questions on what's happening here or what's going on?
Okay. Yeah, questions in chat. Yeah, we're good.
Okay. Let's go on and look at the exercise, which this time I think I got it right, Robert. It hasn't changed on me, but we'll see. So the first thing, again, we're going to bring in data. This is going to be for some homes again, and this is in Iowa. We're going to read it as normal with pandas, and we're going to first, we're going to specify our target. So here, let's look at the columns that came with our data. We're doing a little exploratory data analysis. We've got a lot more than we had before, but it looks like logically maybe the target's going to be at the end here, the sales price. You could do an interesting experiment if you wanted to. I mean, and maybe using something like sales price as a feature, try to predict something else like, another feature. How many full baths does this house have based on sales price and all these other variables? And you'd be surprised, you might do pretty well, actually. Some things you probably would have trouble with, like what kind of utility do they use? But we're gonna try to predict sales price. So that's what we're gonna use here. Again, we're getting a Y as the sales price. And next we're gonna create our features, our data frame that has X and is holding our features. And they give us some hints here. They want us to use these features: the lot size, when was the house built, the square foot of the first floor, the square foot of the second floor. If it has it, I think it puts 0 in here if I remember right, when there's no second floor to a house. How many full baths are in the house? How many bedrooms are above grade, meaning one's above the basement. So if you've got basement bedrooms, they don't go into here. And the total rooms that are above grade. So how much, not in the basement, but above grade. So we put those into here as our feature names, and we pull out our data frame that only has those columns, right? All right, so that worked. And now we want to do some looking at the data. And as you recall from our page before this, where they're describing how to do this, they looked at doing describe and also printing out the first 5 in the head, right, in the header. So they want you to do that. I threw in something else here that I sometimes find really useful, and I wanted you guys to maybe be aware of it at least. It might help you sometimes. But so I'm going to print out these bars in here so we can distinguish the printouts. It actually thinks my column width when I print is here, so it kind of wrapped around. But here's the describe output. So typically, as we saw again, all the features are up on the headers, and then you get all the means and standard deviations and all that for all your numeric types of values. I think when we did this, we had 7, and they're all, I believe, numeric. So we should see 7. 1, 2, 3, 4, 5, 7. Yep. So we've got all the features being coming out from describe here. But if I want to, I could look at these a different way. And sometimes this is really helpful when you have a very large amount of features, or you may have other reasons, but you can transpose the output. And if you know, if you're familiar with transposing, you'll kind of understand this, what it does. But instead of having those features as columns, now the features are my rows, and the statistics about those columns are now listed as the headers here. So it's a very nice way to compare, right? So we know we got an equal number for all these things. Maybe it might be interesting, for some reason we wanted to know, should the first floor square feet be similar to second floor square feet? And you might see some of those values. They give some analysis easier to do when you transpose this output. So it's a handy utility to know about in case it might provide some value for you when you're doing data analysis. Just to remind you again, I haven't done anything to the actual value of X. It's only the output from this describe. So don't worry that you've suddenly transposed X in a way that no longer will fit into your model correctly. Next thing we're going to do is we're going to choose our model type, and we're going to define it, and then we're going to run fit on it. We're going to use the same thing we did before. We're going to use the decision tree regressor, because again, we're doing sales price, single value, numeric value we're predicting. And we're going to feed into it our features and our labels. So that runs, everything's correct here. And now we have a trained model with which we can make predictions. And in this case, we're going to feed it all of the samples. When I say samples, I mean a row of features upon which we can do our predictions. We're feeding all of those into and making our predictions, and they're put into predictions. We're going to print those out, and you can see the values that are coming out of this. Let's see, the first one looks pretty big. I don't know the Iowa market, but I'm going to assume that's pretty big. If we go back to the head of our values, the first one was a 2-bedroom, 2-bath, 3 bedrooms. Maybe not the biggest, but a pretty good size, and very recent compared to some of these. So maybe that's why it would be total rooms. It's pretty big. It's 8. So it could be a pretty big house in Iowa. So a good value. Some of these other ones are larger, so maybe. But it seems logic. It seems to make sense, right? So it seems our predictions are pretty good. But here's the surprising thing. Let's actually print out the real values. So these would be the true values, which are our labels, since we put in our our training data. And if you notice, it cuts off at the third one here, but the first three are exact matches. Anybody have any ideas why that might be? Oh, it's not. It wasn't explained in the introductory information that well, but basically the idea is that it's perfectly fitting our training, and we're able to make the perfect predictions. And with a decision tree that has, in this case, no real limits on how many tree leaves it can make and everything, it's going to get a good fit.
So we kind of memorized basically all the features and their sales price, basically. Is that what
sales price? So this might bring into the next thing is making predictions on our training data and comparing it to our true values and our labels, the right way to evaluate how good our model is. Because this model looks spectacular at this point, right? So I think George is probably in this next section going to get into this a little bit. Anybody have any questions before I turn it over?
So I noticed we didn't do any drop NAs or anything like that here. I guess this data set was a little bit cleaner than the Melbourne one.
Yes.
Okay.
Yes. Or I will say, George, a lot of features here, the ones they only chose 5 or 7. No, sorry, 7. So
maybe they didn't have any missing.
Yeah, I worked with this data set and some other things on Kaggle, and I do believe it may have a few issues. If I recall right, you can run like I said, you can run the is in A and do the sum and see if there are any. But if I recall, there's some like utilities that are missing and a few other weird, like there's some that don't have alleys, and so they have NA in there, and so you have to make sort of you have to decide what you're going to do about that. And it's quite a few that don't have alleys, so you don't want to necessarily just remove them, if that makes sense. So there's other training courses in here where you're going to talk about how to handle data like that. This concept of imputation and other approaches.
Got it.
So here they're really just trying to introduce how do you do machine learning and build, create models and such. They're not really talking about how do you handle this type of data.
Yeah, we have a question. So this is done inside of Kaggle, David. How would you do this in other environments like Colab or Jupyter Notebook?
So basically the same. You've got, this is basically a notebook. You've got, you're gonna have cells like this where you import pandas. You'll have a location where you can, there's various ways to upload data into Colab, and they have a nice kind of helper function on the side where you can kind of search through canned code. And one of them is if you look for import or upload, and it'll show you how to upload data from either your local drive or your Google Drive or Google Cloud storage. So there's nice little ways to do this. You can even if you look at a couple of our credit card fraud coding session that we did, we showed how you could pull data into Colab from Kaggle. So if you want to go back and look at that, or if you have any further questions, reach out to us. But yeah, you can pull data in Colab anyway. This same data can be pulled in. And then sklearn is you import that to get models. Here we're using this decision tree regressor, but there's a whole bunch of other ones that we'll go through. But sklearn, you can pull that into Colab. You don't have to do any kind of special installs. And then all this runs the same, basically the same. You can do the same thing you're doing here. You can also do this on your local machine with Jupyter Notebook. So there's lots of different places you can, as long as you have basically a Jupyter Notebook equivalent. So in Kaggle, they call them notebooks now. They used to call them kernels, but they've switched to notebooks because that's basically what they are. in all the cases, you have things that you can set in your settings. Like here, I'm just using the CPU, but you could run this with a GPU or a TPU. Collab has the same kind of functionality where you set up your runtime. If you need to go get data from somewhere else besides Kaggle, you can turn on this the internet, and it'll let you go out and get it. It's a feature here where you turn it on and off, and so those. There's a whole bunch of things you can do, but it's very similar to Collab. I hope that answers the question.
Awesome. Yep. We've used Colab extensively in our previous sessions, and we've imported data directly from Kaggle using their Kaggle API key. But as long as you have access to the data, you can download it locally. Probably you can import it on whatever environment you use. Usually, Colab, and in this mini courses, we're going to use Kaggle.
Yeah, and I'm happy to go through the pros and cons. There's maybe, they're owned by the same company, just in case, Kaggle's actually is owned by Google. So, but there are some slight differences in the environments and what's allowed in terms of how long your programs can run and things like that.
Cool. And in terms of acceleration, you don't need any GPUs for whatever we're doing now, right, David?
Not for this, no.
Okay, got it.
In fact, I don't think that the decision tree regressor will take advantage of a GPU.
Okay.
You would have to use like the Dask version.
Mm-hmm.
I'm sorry, not the Dask. To use the GPU, you'd have to use the Rapids AI versions.
Mm-hmm.
Yeah. So you can use multiple CPUs. There's usually I don't know about decision tree, but you'll be talking about random forest next, and it supports multiple CPUs. So.
Yep. Cool. So there are no more questions for David, and I'll hand it over to Robert for the next 3 sessions of this interesting challenge. If you don't mind, stop sharing, David.
Yeah.
And Robert, thank you for sharing your notebook as well on the chat.
Yes, so I dropped a link in the chat, which is the notebook that I'll be sharing here. I'll be speaking out of that instead of directly from the Kaggle kernel, but we're solving the same problem. Can I share my screen now? Yes. Okay. Let's see, can you see my notebook, Kaggle Intro ML?
Yes.
Wonderful. Okay, so as David presented, we have a decision tree model, and we have fit it to our training data, and we notice an interesting phenomenon happening in the training data. Now I'm going to go into that in a little bit more detail. There's a couple of dives that are in this particular notebook that were not in the Kaggle course directly. So depending on time, we can move around those or go over them in detail. But let's so these first few cells are just repeating what we had done in steps 1 through 3. I'm going to be focusing on the Iowa data here and not working with the Melbourne data, but we're doing the same tasks on both of them. So the Kaggle course you can follow really either through the learn pages or the exercise pages. So at the beginning of the model validation tutorial, they talk about predictive accuracy and saying, well, you really want to know how well is your model going to perform. So the first thing you should do is look at your observed and predicted values. Maybe just inspect the data frame. And so what do we have here? But it looks like the observed, and we're predicting almost exactly the correct numbers. In fact, exactly the correct numbers for every sample that we see here. So this is in our whole data set here, which is 1,460 rows. How many times do we get correct predictions? We get 1,400 correct predictions. Only 24 samples, only 24 houses in the data set do we ever get the wrong answer for. So this looks like our model is doing absolutely amazing, but maybe there's a problem here. So first of all, we should mention that the accuracy is not a good metric for regression problems where the target is a continuous number. And the reason for that is, maybe we don't really care if we miss the price by $100 or $1,000, right? It's still a really good prediction. We don't want to penalize it. It might make more sense to quantify how much we're missing our price predictions by on average. So when we talk about that, there's a couple different alternatives you could choose from. You want a metric that is continuous, and the mean absolute error, MAE, is the one we're going to choose here. And there's a very intuitive metric, right? You just take whatever the difference is from the prediction, take the absolute value of that difference, and then take the mean across all the samples in your data set. And that's very interpretable, like how much are you missing by on average? An alternative that you could use is MSE, mean square error. And there are some really nice mathematical properties to choosing that instead. Some downsides is it can overweight outliers, maybe tending to move your model towards predicting outliers correctly at the expense of predicting more typical samples. And it can be slightly more difficult to interpret than an MAE, since it is in a different dimension. This is why you sometimes see the RMSE, root mean square error. And one thing we should note is that our decision tree model, even though we're going to be evaluating it on mean absolute error, it actually uses mean square error in the training process itself. And that's because we chose the default criterion equals MSE by not specifying a parameter for criterion in the argument to the decision tree there. So let's look at the mean absolute error of our data set. And we see that the mean absolute error, so on average, we are getting the house price within $62. Not too bad. But what is the problem with in-sample scores? In the text of the tutorial, they offer an example with green doors, and it's not a completely formulated example, but the idea being that suppose all the houses with green doors in the data set are really valuable for whatever reason. Your model might learn to predict, hey, if I see a house with a green door, that's going to be an expensive house, where maybe the green door wasn't really the feature that led that house to be expensive. So the problem with only scoring on in-sample is that you are evaluating data. You're evaluating the model based on the same data that it was used to train on. And you can get a model that is very specific to the data set that it was trained on that does not generalize well to new data. So if we really want to understand how well your model might perform, we want to see how well it will do on data it hasn't seen yet. So to do this, we have to figure out how to give it data it hasn't seen yet. After all, we've already trained it with the entire data set. So we should go back and rethink that decision. And train test split here is a procedure within scikit-learn model selection module. And that allows us to essentially split, as it says, our data into a training set and a validation set. So with this one command, given the original feature data frame and outcome vector, we can split it into training features, validation set features, training predictions, validation predictions. And now we will train only on the training set rather than X, Y. We're going to use train X, train Y. And the training set in this case, we use the default. We didn't specify a fraction to use in the training set. So in this case, we're going to have 75% of our data samples, or about a little over 1,000 in the training, and 300 some will be our validation set. So let's see how well we do on the training set now with mean absolute error. We still do very well, $62 missing by. But now if we look at the validation set, all of a sudden our mean absolute error, we have a totally different picture here. Our model is giving us errors that are average of about $30,000. So in reality, our model hasn't been doing that well. It's just been giving good answers for the exact problems it's already seen. So why are we doing so well in the training set, and why does this performance not extend? So I looked into why is this tree overfitting? So we'll go back to accuracy, which is not a useful metric, but it does provide one useful insight into this model. And we see that the training set, we get the exact prediction 98.5% of the time. The validation set, that only happened in 1 out of 365 samples. So let's figure out why, if the training set is giving us the exact answer all of the time, maybe we can figure out why it's not giving us the exact answer some of the time. So if we look at those 16 samples that it missed, what do we notice that's interesting about them? So what I did was took those 16 samples and sorted them by the predicted price. And you can see that they kind of group together here. These first two both have the same predicted value, and it turns out, well, they have the exact same feature vector. So that's why the model has to predict the same answer for those two feature vectors, even though the actual sales price were two totally different numbers. And because we were training our tree with the MSE, you're going to, for each of these groups here, you're going to get the mean. So for instance, this third set here, we have 3 houses with identical feature vectors. We had to predict the same price for all of them, but it's the mean of these 3 numbers. If for some reason you had chosen a criterion of MAE to train your tree, you'd end up with a prediction of 130,000 for each of these, because it would be choosing the median of these 3 instead. So we see the same phenomenon actually through these entire 16 points. There's, everything is just because it shares the exact same feature vector with something else that didn't have the same price. So, okay, if we have identical feature vectors, maybe the homes are part of the same development project, maybe they have the similar builder, but there's a lot of other variables that we just haven't really taken into account in our feature set. There's no reason to expect that 2 homes with these identical features should necessarily have identical prices. Maybe they were sold on different dates, maybe under different conditions. One of them might have been a foreclosure, or maybe one property is in good condition and the other one needs a lot of work. So for the other 1,079 feature vectors, our model is really just functioning exactly like a lookup table. It's saying, what was the price of that house, and spitting that right back out. So of course it's going to do well in the training set. And it's going to be very unstable when applied to the validation set, because each prediction that it makes is based off of what the sales price of one house in your data set was. So one question is, okay, is this model useful at all? It turns out it is. It does predict, if you had no features at all, you'd get a mean absolute error of 55,000, whereas we did manage to reduce it to 30,000 at least with this rather naive model. However, we can clearly do quite a bit better. Scikit-learn, one of the cool things about it is it allows you to inspect the inner workings of your models. And in fact, for a tree model, you can go in and see all the different decisions and how it routes each sample through the tree. So there's a number of different attributes of your model after you train it. So we'll take a look at the feature importances here first. This is a good one to know about, just kind of showing you which features had the most impact as far as steering your model's decisions and how it lowered the mean absolute error. Looks like year built and first floor square footage are highly valued here. One caveat I would say is that if your features going into the model are correlated with each other, these numbers coming out are not necessarily reproducible.
Say it again, Robert.
So supposing that suppose all your homes are 2 stories, and your first floor square footage is very similar to your second floor square footage, so those 2 numbers are very correlated. You might find some tree models that say your first floor square footage is really important while the second floor square footage isn't. And it's just based on random chance maybe as to which one it's selected for that first split near the top of the tree.
Thank you.
So when you look at the tree class within scikit-learn, you see an object that has all these different attributes. This is all from the documentation of scikit-learn, which you can see at this great website here, scikit-learn.org. Let's go back to the let's see, can you still see my screen? We're looking at the,
Yep, it's the same one, 4, 5, 6 in sample scores.
okay. So some other aspects that you can get from the trees here are number of nodes, what is the child of each node, what feature was used to split on each node, and what is the threshold value that was used for that split. So in this particular tree, we have 2,000 nodes. This is a vector of all the left children, a vector of all the right children, where these are the identifiers of the nodes. If a node is a leaf, then it will just return -1 here towards the bottom of the tree. You can see what feature from among the 7 original features was used. -2 means it's a leaf again, and what the threshold value was at each leaf. So you can really kind of do a deep inspection of your tree to figure out why it's getting certain answers. We can see that the tree is a, I don't know what the technical term is, but every node that has any leaves has 2 leaves. It's a binary tree, I guess, but it's a special kind of binary tree that doesn't allow any of the nodes to have 1 leaf or 1 child. So let's see. One thing that excuse me.
Was that when we initialized our tree? Was that one of the parameters, default parameters, that minimum was 2 or something like that?
Default.
Or is that just caused by model learning, model fitting?
Default to the number of. No, I mean the reason that it's a binary tree where each node has 2 children is just because each comparison uses a single comparator, like a less than or equals, greater than. Any one feature can take part in multiple nodes within the tree, and as you trace down a path of the tree, you'll see the same feature may be used more than once, and it's splitting at different values.
But it's always like a true false.
But it's always a binary split. Yeah.
Okay.
Are there any higher order trees, or they're just implemented as binary trees with longer paths? I haven't seen.
I don't know of a reason why you would train a decision tree for regression with all numerical features anyway, with multiple paths. I believe you might do it if your features are categorical.
Mm-hmm.
So if you have a categorical feature that has 3 values, maybe it makes sense to split on all 3 of them simultaneously. I think what's usually done in that case, though, is you still just find some split of those 3, send 2 values to one and 1 to the other.
Yeah, I haven't seen any ternary or whatever the higher order ones. That's interesting though. Maybe it's an implementation thing. Maybe binary ones are easier to implement and maybe faster to implement on a computer than ternary or higher order one.
It also might be just simply that any splitting that could be accomplished with a ternary node could just be done with 2 binary nodes.
Yeah.
The tree does not have to be symmetric, right? You'll find that some paths through the tree are much longer than other paths.
Mm-hmm.
So one thing that's interesting here is we had 1,095 training samples, but only 1,070 leaves. And if we remember back to our examples up above where we had the 16 samples that were missed, if you look at that, we had 7 unique feature vectors. So that kind of explains 16 misses, 7 unique feature vectors among them. That explains 9 of the missing leaves here, so to speak. But there's another 16 cases in which a feature vectors somehow overlap. So why else might feature vectors be mapped onto the same leaf? And it turns out, well, you can just take a look at what's happening on those cases as well. So I'm looking at all leaves that have more than 1 training sample routed into that leaf. And you see what happens here is that, well, they end up with the same predicted price. So even though the feature vector may have been different, if you end up with the same predicted price, there's just no reason for the tree to split any further because it's not going to lower MAE by doing so, or MSE by doing so. So they're all printed out here, but if you look at the number, the difference in the length of that data frame minus the number of leaves, you end up with an explanation for the exact difference between the number of samples in your training set and the number of leaves in your trees. So that explains all the leaf nodes that contain more than a single sample. And the interesting question here is, well, what are the consequences of a fully grown tree model like this? You know, do our predictions, how might this lead to poor predictions? So one thing you can do in data analysis that's a useful tactic sometimes is to see, okay, where's my model doing poorly? Take a case where it does really poorly and see if you can figure out why. So in this case, we can sort by the actual absolute error of any particular sample. And we see that the worst case here is one home here at the bottom, which was built in 2008, has a first floor with 1,700 square feet. And we predicted that it's worth about 150,000, but it actually sold for 367. So it's off by more than a factor of 2. That's the worst prediction in our data set. No other house missed by more than 200K. So you can dig back in. I won't go through all the details of exactly the wrangling that goes on here to figure your way into the tree and figure out exactly what's going on here. But there is a method called decision path that gives you that access and tells you, well, that particular node went through these nodes on its way to where it was going. And this particular one had 10 nodes, so it only took 10 branches before it reached the leaf. So we have 10 branches. Actually, most of the examples take more than 10 branches, but this one only took 10. So maybe we can look at the actual decisions that were made. So in at the root of the tree, the very first decision that gets made is the year more recent than 1985? If so, you route it one direction. Otherwise, you route it a different direction. Is the first floor square foot less than 1685? And so on. You can see all the decisions that were made as you progress down to get the prediction from this tree. So another thing that you can do is see how sensitive is our tree to small changes in the input. This can be a really interesting thing to do. A couple little steps here, and you can see that if your year built is 2008, it predicts a value of 150,000. If your year built is 2009 with the exact same feature vector otherwise, you get $400,000 predicted. So this shows you the high sensitivity of these tree models and how they can be so sensitive to just one tiny little perturbation of the input data vector. We can actually look at all the different years in the data and just change the year for all the different possible years in the data set for this exact same feature vector otherwise. And we see it's predicted for a pretty low price most of the time until the year goes over 2009, in which case it goes really high. And keep in mind that our house was sold for a high price, but in 2008, right here, right below.
Did you predict the economic crisis of 2009 with this data set, or is that a consequence of the crisis? Interesting.
I suppose that will be a follow-on. If we can predict that economic crisis from this Kaggle housing price data set alone, I'd be impressed.
I'm interested in 2020. Can we run it?
So let's see. So what we should do now is figure out, okay, how can we make these trees less specific? Can we improve generalization if we just build a smaller tree? And we go back to our original picture here, and this was a really simple tree. Maybe a tree that's a little bit closer to this one won't overfit quite so badly. So one thing I did down here to kind of get an illustration of how many samples are involved in each of the decisions that are made is to look further at the path that one really badly predicted node took. And at the top, at the root node, all the training samples go through there. But as you get down, it doesn't take too long before you only have a very small number of houses that you're using to predict. So down, when you get here, you have 20 houses in your sample. You're predicting the mean of those, and then you're routing it somewhere else, and you're predicting 7, and then you're basically just saying, what was the value of this house? And that is the answer. So the prediction that was made for a really poorly predicted house was all based on one other sale price. So this is due to overfitting. A little bit of text here to explain basically exactly what they talk about in the Kaggle course. Pictorially is probably the best way to see what's going on. If you have a model that is very complex, like these very deep trees, you can train them to get perfect performance here. The error just keeps going down no matter how deep the tree gets. And eventually, though, the validation set's just not going to be able to do that. For a very simple tree, you get underfitting, which is the case where the model is just not able, if you make our tree very short, it's not able to divide the houses up into very many distinct groups. You know, this particular tree right here is only capable of 4 distinct outputs. So you're going to have a lot of bias or underfitting in this tree as compared to the overfitting in the fully grown tree. Where the validation and training performance start to diverge, you'll eventually get to a point where you have a minimum in the validation mean average error. And that's the point where you want to shoot for. Now, the question is, how do you find this point in your data set? One way to solve the overfitting problem is to try to make smaller trees, as we talked about, but now we're going to actually implement that. Decision tree regressors have lots and lots of parameters, and many of them all kind of do the same thing, which is to make the tree shorter in one way or another. Max depth, min samples split, min samples leaf. Every one of these 8 parameters listed here changes the number of leaves, depth of the tree, etc. And every one of them in the default is set to grow the tree fully. So what we should do is just change one of them if we want to make a simpler tree. And in the course, we chose max leaf nodes as a hyperparameter to vary. They define a pretty cool helper function here that just allows you to loop over the MAE. You try a number of different values for max leaf nodes, and we find that in this case, we get 100 has the lowest MAE. However, it's not too sensitive to max leaf nodes. If you choose a number that's in the right ballpark here, within a factor of 2 or 3 or so, you're going to get a pretty good MAE, pretty comparable. Best tree size was 100 there. So in general, you're not going to do what I've got in this notebook right here, but because decision trees are so quick to train, I actually did an exhaustive study and tried all possible values of max leaf nodes because I was kind of curious to see how that behaved. I won't go into all the details here because we want to get through this in a reasonable amount of time. But the first plot here just shows a zoomed out view of what's going on here with the training MAE versus validation. It's a little bit tough to see here, but the minimum is kind of in this area here around 70. And it slowly increases over here. Maybe you want to zoom in a little bit, which we do here. Let's see. One thing that could be interesting to note is that there seems to be some correlation from one value to the next. The only reason for that is we're using the same random state in every one of these. If we were to train completely new trees each time, you'd find a much noisier behavior here. So now if you think about, what should you expect to happen, you might visualize a curve through here, and you'll see that one, the curve doesn't change much. It's really flat down here for hundreds of possible values. And 2, it's kind of impossible to predict whether you're going to get a good value because it's so noisy. As long as you're in this region, you're fine. So the short summary of that is don't spend a ton of time trying to optimize your models to get the perfect value there. because what might be the perfect value on your validation set is just going to be the perfect value for your validation set and is not necessarily going to extend to different data in a test set or in a commercial use or whatever you actually want to use your model for.
Robert, what is the difference between this graph and the previous one?
So what I did differently in this plot is, and I didn't really talk about it too much, but the difference is right here. Instead of using random state 1 for every one of these trees, I changed the random state. And I just chose to just copy the max leaf nodes in there as the random state.
Got it.
Just not because that has any meaning, but just because I needed a different number, and max leaf nodes was the loop variable. So one thing that might be more useful than doing hyperparameter tuning on decision trees, maybe try a completely different model. So if you do a random forest model, let's learn a little bit about random forests. The course doesn't present much detail on them, but there are many places to go to look for more detail about random forests. Leo Breiman's paper here is where the original model was presented. Some improvements to it in this other paper here. The concept is, what if instead of building one decision tree that has some cliff in it where it makes a completely different prediction for year built 2009 than year built 2008, what if we train a whole bunch of different trees, give each one a different data set, and then have those trees average their predictions? If we do that, we shouldn't expect these large cliffs because each tree will have been trained on a different data set. The idea is to get behind the concept of ensemble models, where you can often lower noise by combining predictions from multiple estimators. And then that is basically where the logic that Breiman was using in developing his model from decision trees. So question, we only have one data set. How can we get multiple trees with different data sets if we only have one data set to start with? And there's a really neat statistical idea behind this, and it's called bagging, which is short for bootstrap aggregation. And the basic idea here is you might have a data set that looks like this, and you're going to reach into that data set and sample from that data set with replacements. For each of these bootstraps, you might train a decision tree with these samples, then you might train a different decision tree with these samples, and you train a different decision tree with these samples. And because they're sampled with replacement, you can get some pretty different distributions from one tree to the next, even starting with the original data set that only had your 1,000 points in it. This is a great little visualization from a course called mlcourse.ai, which is linked to on Kaggle, and you might be interested in checking it out. It goes into some more detail on some of these concepts. I just found, I haven't taken that course myself, but I really liked this visualization, so just took it from there.
Robert, you're replacing, is that like, does it have some kind of statistical feature behind it? Or what is the reason that you're doing sampling with replacement? Or is that
so the reason that you're doing sampling with replacement is you want these trees to be somewhat different. And if you sample without replacement, then you're going to only get, okay, there's 2 yellow samples in here. But once you take the 2 yellow samples out without replacement, you won't be able to get the 3rd yellow sample here. As long as you sample with replacement, your tree will be unbiased, and it will also be as decorrelated as you can get from this particular sample set. So one tree could have a lot of yellow, another tree could have a lot of purple. They're all drawn from the same distribution, but training each tree with a slightly different data set drawn from that distribution can really improve the ability of your model to generalize and not be so specific to one tiny cliff that you might see in that original decision tree.
The tree will actually, let's say, I was coming from the perspective that you might see the same record twice. The tree will actually use those 2 records as individual records, or will it remove any duplicates?
Correct. They'll actually treat them as duplicate, or they'll treat them as individual records. So it'll, if that purple sample gets in here 3 times, that means it gives triple the weight to the purple house from the sample. So it seems counterintuitive, right? Like each one of these trees is going to do worse than your original decision tree, because this original decision tree had all the data, whereas this one is really overweighting one particular house from your data set. And this one is really overweighting a different house. But by overweighting different house for each one of these samples, what you have accomplished is you have decorrelated the trees. Tree 1 is likely to make very different predictions from tree 2. And if tree 1 and tree 2 each make okay predictions, and we have a lot of trees that each make okay predictions, by combining the wisdom, it might actually do pretty well. So maybe one analogy to this could be, if you have a coin that might be slightly unfair, how might you determine if the coin is slightly unfair? Well, you could get a whole bunch of measurements done on the coin and try to see if it's imbalanced weight-wise, but there'll be some error in your measurements. Another thing you can do is just flip that coin many, many, many times. Those measurements, those are individual measurements of the bias of the coin. They're poor measurements because you only get yes or no for any one particular flip, isn't going to tell you anything. But once you have a whole bunch of those measurements, you can get a very convincing answer as to whether the coin is biased. And what makes that a convincing answer is it's crucially relies on the fact that the measurements are not correlated.
Got it. I like this image because it also ties up with your greenhouse or green door picture above. You actually have a house that shows up 3 times the purple one or the red one or the yellow one.
Yes, color is always a very useful visualization property. So another, and as an example of bootstrapping, I thought this might be a little bit more illustrative, although certainly less visual. So one thing that this example does not do is it does not show the most typical use case for bootstrapping, in which you have the exact same number of samples here as you had in your original data set. So typically you'll bootstrap and you'll say, okay, if I had 12 points here, I'll get 12 points here sampled with replacement. There's statistical reasons for choosing that value. But I just wanted to show an example where that was the case. So I'm taking the 26 letters of the English alphabet and just showing different bootstrap samples and what can happen. So this is 26 letters. This is 26 letters. This is a different 26 letter sample. This is a different 26 letter sample. And maybe you can take a sample like this one where you get the L appears 5 times, but then there's another sample down here where the L doesn't appear at all. So each tree in this forest is trained with a totally different group of data, and each tree is going to be looking for something different as a result when it goes to make a prediction. So let's see how well we do with the random forest regressor, just straight out of the box in scikit-learn, random forest regressor on the training set, and then we're going to predict on the val set, and you get a MAE of 21,800, which is significantly lower than the 29,000 something that we had for the decision tree model, and even the 27,000 something that we had for the tuned decision tree model. Random forests work pretty well right out of the box, but you can also tune them. I actually decided to play around with that, so tuned one of the parameters of it, which is called max features. And max features is, there's another source of randomness in random forests where you can actually down select which features are even being considered for any given split. So I ran some computations on that, decided to run it 100 different times. And the reason I thought that might be interesting is that run 1 here, where our random state was 1, and we got that 21,800 value. Turns out that was a somewhat fortunate result. If we run with max features 7, which was the default here, many times, the actual mean is over 22,000, and the standard deviation is 180 something. So this is almost 2 standard deviations below the mean. And turns out that our optimal value of this parameter is 4. So this is just random forests work pretty well out of the box, but you can do a little bit of tuning on them too. Now this MAE actually turns out to be worse than our original one, which was not tuned, but I think this MAE was somewhat fortunate here. So if you run it on the test set, on a test set with new data, you're more likely to get a value closer to 22,000 here. So I know we kind of sped through this notebook. It's all online if you want to go through it in more detail. I want to make sure George has some time to talk here too.
Yeah, thank you, Robert. I had one question regarding the random forest. I was under the impression that you I like the way that you explained it very well. That basically you're saying that the data set is split in different ways, and the data set drives different trees on how they construct it. Is there any other way you can go the other way? You expose trees to the exact same data set, but you train them or you construct them in different ways. Maybe you prune them, or maybe you limit how they develop during the training, or maybe that's not the default behavior in scikit-learn.
Not totally sure I understood the question. You're proposing a forest of trees that have different depths or different complexities?
Yeah, so they're all exposed to the same data set, but they have different hyperparameters. Maybe they have a different max depth, or maybe different decisions based on each node. So basically you're training a completely different model, but you're exposing it to the same data.
So I think that will not work as well as the concept of under random forest. And the reason for that is that if you're giving every one of those trees the same data set, even if you're changing the models slightly, there's likely to be a lot more correlation in their predictions than you'll get from bootstrapping the data fed to each of those trees in this fashion.
Got it. Awesome. Thank you, Robert. Any questions for Robert? If you don't mind, stop sharing, Robert, in the meantime. Awesome. Thank you. I like that you went your way there and took a deeper dive. I love that. Thank you so much.
Well, I think one of the reasons we're going through this exercise is to add some value to the Kaggle course. So the Kaggle course is a great place to get started in machine learning, but sometimes it's helpful to also see what you'll be able to do if you just dig in a little deeper.
Yep. Let me share my screen. I wanted to share with you a resource that I found online. I was also pursuing this. Can I visualize what I'm looking at? So I found this resource online, and basically the decision tree. So we use the decision tree regressor. We're trying to predict the continuous value here, but there's also a decision tree classifier when you have discrete classes, when you're trying to classify something. And all of them have some built-in methods. One of them is the default one, which is text-based, and there's some other ones that are visualization-based. I just wanted to share them with you real quick in case you wanted to take a deeper look. So I'll skip to the regression part. So the simplest thing you can do is you can just look at tree. So you have to import from sklearn tree, and from tree you have to use the method export text and give it your decision tree regression. And there you'll see almost like a man page, like a text representation of your tree and the different nodes and the feature and what is the decision, how it's made. Another one is you can use the plot tree, and that will give you the different features and how it's broken apart. So you can see it here. And I think the color means a higher value, or I think it's correlated to the value of the predicted field. Yeah, color of the leaves corresponding to the predicted value. Another one is another package, a little bit more detailed. It's called D3Vs. You have to install it though, and it gives you a little bit more information on how things are broken apart. Cool. That's what I wanted to share. So let's go to, so we covered 1 through 6, and then this course has a 7th one, which is competitions, and as well as some bonus ones that will go together on AutoML. So for the competition, I highly encourage you to check it out. You fork a notebook here from Kaggle on house price competition again. And let's take a look. I think it's the same data set that we saw. Let me refresh my memory. Yeah, from Iowa, I think. Yep. And so when I first tried submitting it, I got something in the 20,000 something MA for house price, I think. Then what I did is, okay, let's do a little bit more feature engineering. So then what I did is, let's consider more features. So in Kaggle, you can use different versions, and it looks like I'm using version 2 here. And the difference for me was I got rid of all the records that had any missing values for any of the fields. Later on, there's a feature engineering course that does a little bit of better job instead of dropping the entire record. And then I considered, yeah, all the features. So I said there's 81 features, I think, yeah. All of them for regression here. And isNA is the method that David mentioned. You can see if you have any missing records here. So I have 1,400 records with 81 columns, a train and test split. Again, it's 75-25% split. This is a single tree. Let me see if I did any other optimizations here. Oh yeah, I think the other optimization I did was looking at different max leaf nodes and just picking that one for the final model. And that one gave me an MA of about 24,000. And random forest, as Robert mentioned, out of the box, just give you significantly better MA. Another package that I used was this permutation importance. I think there's another course that later will take a deeper dive, but that will give you a breakdown of all your features, similar to what Robert did, of what is the importance of each feature for my tree. So in this case, something called overall quality is highly important for my tree, or for my random forest. Then living area, then basement square feet, second floor, apparently is higher than the first floor, and so forth. And you can see all the different features here, how important are they to making a decision. Zoom out a little bit. Cool. Then the other thing the only different part here that we did was, so we have a training and a validation set. In the end, before we submit it for the competition, we actually combine the training and the validation set to a larger set. And we train a new random forest regressor on the entire larger data set. That's the only difference here, so that we can maybe take advantage of those unseen records in the validation set. And I think for this version, I think I used, yeah, the entire 81 features here. Then let me go through the submission process real quick with you. So once you create your notebook, once you get your output here, you'll see the file that you've created. There's an option that says submit here. And what that will do is, since this notebook is actually linked to the competition, it will auto submit it for you. If it's already not linked, let me see if I can visit. Yeah, let me visit this competition right now. Then if you just go there, so you do your own analysis. It could be in Colab, it could be in Jupyter Notebook, it could be anywhere. Then when you're done, usually here, if you go to the end, there should be a submission under data maybe. Should be a submission file that gives you an example of, and here's a description of all the fields. But there should be a submission.csv, yeah, sample submission.csv. And that one will give you the format of how should you submit your data. So you only need two columns, the ID, which is the ID of the record, and what is your predicted value for that house ID. And then you can do it from the API, or you can just go to submit predictions. And it will ask you, okay, upload your submission file. And many competitions have different rates or different thresholds on how many times you can submit a day and so forth. And it should be a CSV. It can also be a zip or archive if you prefer. And they expect, so they have a specific test data set with 1459 rows. So they expect exactly that data set to be present with your predicted value. And it should have a header row. Then once you do that, you can see here there's a leaderboard. You can see it here. You can also jump here where you are on the leaderboard. And it will tell you, whew, you're somewhere in the middle of nowhere. Let's see, where am I? 26,000 something. Yeah, 26,300. My MA is about MAE or MSC. I think if you look at the description of the competition, I think they describe you if they use MA or MSC, but this looks like MA, right? It's too low to be MSC. Yeah, 16,000. So this was my version 2 one. So version 1 was, and if you link it from a notebook, it will actually show up here. My version 1 was just using those 6 or 7 features, and my version 2 was using all 81 features. And most of them don't have notebook. I was interested in, some of them have notebooks, some of them don't. But if you want to look at, okay, what else are other people doing? Like, this is the beauty of it, right? You can go here. These are, I think, the default ones that from the Kaggle Mini Courses. But you can see.
I'm guessing the ones that scored 0 don't share their notebooks.
Yeah. Let's look at. They don't. Yeah. So there's many of them that score 0, right? And David, you mentioned something on Slack that somehow they have a way to probe the test data set. I don't know how.
Yeah, they've gamed the system to probe the test. I'm sure of it. There's often, the guy down in the 11th might be a real submission.
So is it just using the data that you have in the competition, or are you using external data, you think?
Well, sometimes, like in the case of, like, there's one called predicting digits or something like that, where it's the MNIST data. Mm-hmm. They've just gone and externally got all the full set and trained on the full set, right? So from NIST, right? So they can, but here they probably figure out a way to probe the test data somehow and figure out what the results should be. Who knows how they've done it, but they haven't predicted a score of 0, I'm pretty sure.
When I did this course about 1.5 years ago, the number 1 spot had whatever the mean error was of about 11,000, which sounds like a real number.
Right. So they'll reset this every 2 months or something, I think. This is an ongoing thing because it's just for training, right? I mean, this is not a real competition, right? So.
But the test data set that your algorithm is trained on is unseen, right? And also changes over time, I assume, or is it the same? I don't know.
It's unseen, but you see the scores, right? So if you change the value, there's a way to track how your score changes. And so they work out they work out what they need to switch to get to the perfect score, right? It's sort of like,
Got it.
it's called probing the tests. It's a, you know, it's a game.
Yeah, I think there was a famous example about a year ago or so where someone was found the same images from the test set on some other website and was able to like link to that site's classifications or something. And then they disguised their use of that data in the code that they submitted.
Yeah.
And it took like an investigator to like find that that they had cheated.
So this
So a couple
test,
things.
yeah,
George, a couple things out. There is another way to submit from the Kaggle API itself. Like, so if you're in Collab, you know how we can download directly from Kaggle. We can download a data set.
Yep.
Competitions. You can also submit directly from command line in Collab.
using this command here.
Oh yeah, there you go.
Yeah.
Yeah. So
Cool.
that's a nice feature. You don't have to go over and manually copy files or anything like that.
But going back to the leaderboard, so there's two leaderboards, right? A public and a private one. For the public one, is the test data set the one that's available here, and you can do whatever you want with it? Got it. And the private one is another completely different data set that you don't have access to.
Right.
I'm surprised there's nothing on the private though. I guess because it's open. I don't know.
So this would be, it's configured for like other types of competitions that only go a certain amount of time, and then at the end they run your data against the private leaderboard to get the final winners. But this one is a basic one that never ends. I don't think there is a private data set actually.
Yeah, and here there are some limits, right? So there's no deadline. You can do 5 entries per day. You can form teams, and your teams can be as large as you want.
Mm-hmm.
One account, okay.
So if you go back to notebooks there, you can sort at the top. It defaults to hotness, but you could do by score, votes, best score. This will show public notebooks and what their scores are.
Mm-hmm.
Well, there you go.
Stacking in something.
So you can see
there's
there's
11,000. Okay.
Yeah. So there's private notebooks that are obviously better than that, but this is a public notebook. You can see how they got that score, right?
Got it.
And if you look at your own submissions, your own notebooks, once they're scored, it'll show your score at the top also, just like this one has.
Yeah.
You go to your work, and then instead of public there where it says your work, see it to the left.
Oh, here.
Yeah.
Yeah.
So if you click on that notebook, it'll show the score, right? Because yours is.
It also shows, yeah.
Yeah. So see your public score up there. Yeah.
And you can also you can see it here.
Right. Right.
Cool. I like this. This was a good one. There's an advanced version of this house pricing competition I will go through, but this was a good start, I think. Cool. Any questions about how to submit? How to submit your data to a Kaggle competition? Oh, you posted some links there, Robert. Thank you. Cool. Then the last thing I want to talk about.
The link I posted was how not to submit to a Kaggle competition.
Not to submit. Okay, good to know. Thank you. So the last section is there's another one actually on Titanic, which is you can basically do your own work on Titanic dataset. But I want to spend a little bit of time here on this AutoML section, which basically takes a slightly different approach. So you've seen that so far we've gathered the data, we somehow prepared it, we got rid of NAs, maybe we did some other smarter feature engineering. We selected a model, which we started with a single tree, decision tree, then we tried this random forest. We trained the model, we evaluated it, probably on a validation set. We used different metrics like MA or MSC. We went back to the drawing board, okay, let's fine tune it a little bit. And then let's get predictions, and then those predictions we can either use them as for our task, or maybe we can use them to submit them on a Kaggle competition. So there's about 7 steps that we had to go through this challenge. And what we've seen so far is we have to do this step by step, one by one. There's a collection of tools called auto machine learning or auto ML, and there's pros and cons of using them. If you come from Keras, that one has its own. So Google Cloud has its own solution as well called auto ML tables, and it's used for structured data. So if your data can fit on a table, then you can use one of their service, and it's a paid service called Google Cloud Auto ML table. That's what we're going to look today. That basically takes care of steps 2 to 7. So you just need to spend time on gathering the data. Could be a Kaggle data set, could be your own private data set, at home or at work. And as long as it can fit, as long as it looks like a table or can fit on a table, you can use this service. So again, this is a paid service, and for this project, I think they mentioned this New York taxi, but I used it on the housing data set as well. And if you want to take a look what this is, so there's something called AutoML tables wrapper that basically act as a mediator between your Kaggle notebook and the Google Cloud. So before you do that, there's specific steps here on. There's a starter notebook here on how to enable this service from Kaggle. So let me see. Have it here? No. Oh, there it is. No. There it is. That's my submission. Let me go to my notebooks real quick. So yeah, so here you can see your notebooks. I wanted to look a little bit at the that wrapper. There you go. So this wrapper imports some modules from Google Cloud, and one of them is storage, because you need the data to be stored in what is called the Google Cloud Storage and GSC, and this AutoML feature. And you're going to need to create a project ID, which usually you have. You create a new storage location under bucket name. Where is the path of the training set? Where is the path of the test set? Which column are you using for target? In this case, would be the sales price. Which column are you using for ID? And it's usually a good idea to exclude that. Otherwise, it could be maybe your model could. That's the green door basically example, right? Your model could somehow figure out that all the houses with IDs, I don't know, ending in 0 somehow have a specific behavior in the sales price. So you want to make sure that something as an identifier is excluded from your training process. What is the name of the model? Which region your model is running, and so forth. So there's a lot of code here, but you don't have to worry about that. You just call this wrapper. Let me go back to my previous example. Actually, let's go to the model itself. So within Google Cloud, if you're familiar with Google Cloud, under Home, there's something called Tables. It's actually under the Artificial Intelligence block. So you have AI platform, recommendation, natural language processing, so tables. And under Tables, you have data sets and you have models. So data sets is anything that can you store on a Google storage on Google Cloud Storage, and this is where you, let me show you how that looks, because I have another one open here. So yeah, this is my bucket, and it contains the training set, and this one a little bit, and the test set, and then these folders are created by my model as it's run. So let's take a look at some of these models. I'll start with the very first one that I ran. So I ran it from Kaggle the first time. It used 79 features out of 81. So it excluded the ID column and the sales price. Yeah, targeted sales price, optimized for RMSC. The best MA it got was 15,000, which is pretty good. It's a little bit better than what we saw before. And it also gives you feature importance of what features were the most important ones. For mine, my random forest picked the second one, and the third one is the most important. This one picked another one, so that's interesting to see. I wanted to take a look at how this model works under the hood. So I was able to find, so if you take a look here under models, I think, or see full evaluation, you can actually look at some examples here. So I wanted to see, you can't really tell exactly what and how it was trained, but you can see it's some kind of a, so this is a model system, gradient boost decision tree, and some kind of regularization. So there's several parameters here, and each one uses a slightly different setup to train. So this looks like an ensemble model. So you see here, max tree depth is 9, 400 trees, L1, L2. I don't know how they apply in decision trees, but we've seen them in deep learning approach, where you basically penalize models that have excessively large weights. So basically, they tune to some features that maybe are not the right ones. I'm not sure if they apply to decision trees. Do you know, Robert?
Did you say that this this array that we're looking at here, 0, 1, 2, 3, each one of those is one model of a larger ensemble?
Yeah, I think so. There's like 24 here.
Yeah.
And each one, if you notice, has a hyperparameter block. So this has 300 trees, 0 L1, 3. This one is 300, 0, 3 again, max depth. Let's see what is different. 6, 6. They look similar.
But they'll be different models because they'll have different bootstrap samples on the trees the same way random forest does.
Yeah, this one, yeah. So this is what I was asking you about. So are you just changing the data set and then let the models develop on their own, or are you also somehow hyperparameter tuning the models itself on the side? So this one looks different, right? This one has 300 trees, this one has 450 trees, and it's doing some kind of hyperparameter tuning here. I don't know what this tree complexity is. Yeah, 9. This is just me being curious. Okay, what is under the hood? But I don't know. Maybe there's a nice blog post that explains how this works. Cool. Then once you train your model, which by the way takes a while, and on the Kaggle notebook it says you should train it for 2 hours. And there's a cost for that, and you'll see I have a report for cost here. But the first model I trained was give me a MA of 15,000. So R2, the higher R2, the better, right? It's a Pearson correlation that tells you how well your labels and predicted values are correlated. Then what I did here was, one issue that I had was, let's talk about prediction. So the way you predict it, you go under test and use. And under, in this case, my data was a CSV. So I chose a location of where my test data set was. Let's say here, select And where do you want to generate the result? Let's say another cloud storage bucket. Let's say here. Select, and you do send batch prediction. So when you do that, it takes a while. It takes about 4 minutes to do this. It uses the model that it was trained on to predict the sales price for each of the records that you have in that test.csv. And you see that in your storage here. So you'll see a new folder being created here soon, once that is done. But the issue that I had for many times was, if you go to this folder, you'll see a table CSV, which is basically, let me download it. It's basically the training set. And the very last column should be the predicted sales price. The issue that I had was, let's see, let's go all the way to the beginning. If you notice, I should have 1459 records, but in this case, I have 1449 records. So I'm missing about 10 records. And if you go back in this error.csv, download it from here. So these are 10 records. Let me maximize this. That for some reason the model couldn't run, and it excluded from my final output. This is the ID. These are all the features, and in the end, you'll see why it failed. Okay, so the model by default is trying to figure out, based on the training set, how many records have null values or not. So when it was trained, if you look at, for example, at kitchen quality, it was trained, it had only seen records that had a value for kitchen quality. In the test set, we got something, like if you look at kitchen quality here, probably it's missing. Which brings us to this overview of the model. Go back. If you go to my model or train, so you'll see you have 49 features that are categorical, 30 of them are numeric, 2 of them are, I don't know what text is. It's not categorical. But by default, based on the training set that you had, the model saw that first floor square feet didn't have any missing values. So by default, it was trained on data that it assumed would always have a value. So same for everything else, if you see here. And the good thing about this is if you click on it, it will tell you the distribution. Let's click on another one. I don't know what that means. Let's pick one, maybe that we can kind of understand.
So if it sees any sample in the data set that is missing a particular feature, it will train trees robustly to be able to ignore that feature if it needs to?
Yes, exactly. That's what it's doing. I don't know if it's doing that or it's doing some kind of a pre-processing to take care of null values.
But anything that it doesn't find any nulls in the training set, it just assumes it's always going to get.
Yeah, it assumes that it's always going to be there. But when it sees in the test set, when it sees a record with, let's say, null value for first floor square feet, it doesn't know how to evaluate it. And it gives you that error. At that point, you have two options. You can either set this to nullable and train it again, which will take another 2 hours and some amount of money. Or when you submit it, before you submit that test CSV, you go and you edit the record to make sure that it's not null anymore, but maybe you add some kind of a value, maybe 0 or NA, or I don't know, depending if it's numerical or categorical. So I followed the approach of, okay, let me retrain once or twice. Hopefully I'll get out of this weird situation. But every time I did, I was running into the issue. I have less and less records in the test set that for some reason are failing. And in the end, I just manually changed a few features so they're not null. And the reason is, if you go to reports, let's see how much this costs. So I ran this the first time, and GCP gives you a discount. So for 2 hours, it costs like what, $38. Then another one, another $33, and another one, $30. I was like, no, that's it. I'm just gonna change my test.csv here. So good thing there's a promotion going on. I'm not gonna pay anything next month, but yeah, that's something to keep in mind, right? That this doesn't come for free. There's a nice blog post, and there's a nice documentation for all this, but there's some more fine tuning you can do. I find it interesting. As long as your data can fit in a table, you know, you can use this service. Any questions about this? Oh, I have more information here about pricing and all that. So yeah, model training is $19 per hour. So we use 2 hours. And deployment, it costs a little bit per gigabyte per hour. So I shouldn't keep it for a while there, I guess. And also doing batch prediction. So when you do batch prediction, when you upload your test set, there's a cost for that as well. So I'll share these links on our chat as well. So let's go to the second competition. And so this is a slightly different one. It has more features, I guess, this data set. So here, using that AutoML, the score here, I don't remember what exactly is the score. It's not MA, right? It's something else. F1. Root, oh, okay, RMSE. No, root mean square logarithmic error. Okay. That's why the numbers are completely different.
That's so it doesn't overweight expensive houses, I guess, relative to cheaper ones.
Okay. But there's no 0 here, you can see, so. But maybe logarithmic, right? So you're never going to see 0, I don't know. It's funny that the top ones are stuck at that value, 4.4. Yeah, let's see.
Yeah, I mean, in theory, one could submit the perfect answers, right? And then your logarithmic error should be negative infinity.
Mm-hmm. Yeah, and you can look at discussion, notebooks, rules, similar to the other one. Yeah, and a short description of the different features here, and a sample submission. Cool, that's what I had. Any questions for us? I'll stop sharing here. Next time we meet, we're going to talk a little bit about pandas. And then after that, there are some other interesting sessions. So I encourage you to check us out. We will try to do some more heavy topics on Wednesdays and some other related topics on Fridays. But the goal is to go over the entire Kaggle courses. So if that's something useful to you, join us. If you only want to tune in just for specific sessions, feel free to do that as well. Cool. With that said, I know there's a debate going on in a few minutes. I know people want to tune into that. With that said, thank you everyone for joining us, and we'll see you next time. I'll stop recording here.
Thanks everyone for joining.
Thank you.